Hey guys, Mr. Backer here. In this video, we're going to look at solving trigonometric equations. Now, as we're looking to solve some trigonometric equations, we're going to treat it sort of like we did with those trig expressions and work on simplifying them down to make the math easier on us. Now, as we're looking at solving a trig equation, we're going to be using the unit circle to help us out, and getting things written in terms of sines and cosines can be helpful because as we're solving these trig equations, our last step is usually going to be to do an inverse trig function, and it's easier to find inverses of sines and cosines using the unit circle than it is working with some of our other trig functions. So in this example, we're going to look at finding all the values for x on the interval from 0 to 2 pi that solve this equation. Cosine cubed of x over the sine of x equals the cotangent of x. Now the first thing I'm looking at is that cotangent on the right-hand side. I said that it could be helpful for us to get things written using sines and cosines. And we've got a quotient identity for the cotangent that says that cotangent is equal to cosine over the sine. So I can replace that cotangent on the right-hand side with cosine of x over the sine of x. Now what I'm going to do is I see that we're dealing with fractions on each side of our equation, and each one of those fractions has a denominator of sine. So what I'm going to do is multiply each side of my equation by the sine of x, and what that's going to let me do is cancel out those denominators. So now my equation just says the cosine cubed of x equals the cosine of x. Now what I'm going to do is take this cosine of x that's on the right-hand side, and I want to get all my variables on the same side. So I'm going to subtract that over to the left-hand side. So then my equation will say cosine cubed of x minus cosine of x equals 0. But then we're going to be able to take out a GCF because each one of my terms has at least one cosine in it. So I'm going to factor out a cosine of x, and that's going to leave me with cosine squared of x minus 1 equals 0. Now as we look at what's inside of our parentheses, that's really close to one of our Pythagorean identities. But what we're going to have to do in order to get that to look like our Pythagorean identity is we're going to have to factor out a negative 1. So we've got this cosine of x that we already factored out. We're going to factor out a negative 1, and then what's going to happen is I'm going to rearrange this at the same time. But when I factor out a negative 1, that turns this negative 1 into a positive 1, and it turns this positive cosine squared into a minus cosine squared of x equals 0. Now I'm going to take this negative 1 that we just factored out, and I'm going to multiply it to this cosine. So we have negative cosine of x. Now what I'm going to do with what's inside of this second set of parentheses, now that looks like one of my Pythagorean identities. So I can replace that with the sine squared of x equals 0. Now just like when we do factoring with an algebraic equation, a trigonometric equation works the same way, where now that we have this factored out, we can take each individual factor and set them equal to 0. So we've got this negative cosine of x equals 0, and we've got our sine squared of x equals 0. Now to get rid of this negative in front of my cosine, I'm going to divide both sides by negative 1. So I get the cosine of x equals 0. But now I want to get my x alone. So in order to get rid of this cosine on here, what I'm going to have to do is the inverse cosine. So x is going to equal the inverse cosine of 0. And now we're going to think about our unit circle. And the cosine is the x value from the ordered pair. So if we're trying to find an angle on the unit circle where the cosine, the x value, is 0, there's two places where that's going to happen. That happens at the angle pi over 2. And it also happens at the angle 3 pi over 2. Now we still need to solve this sine squared portion. So in order to get rid of the squared, what I'm going to do is square root both sides. So this is going to say the sine of x equals 0. And now we have to be a little bit careful because we're saying that the sine of x is going to equal 0. But if we go back to our original equation, we've got the sine of x on the bottom of our fraction. And if we let the sine of x equal 0, then that means that we would have 0 on the bottom of this fraction, which we're not allowed to have. So this sine of x equals 0 isn't going to give us any actual answers. We would get undefined values at those zeros. So our only answers for this equation are the x equals pi over 2 and the x equals 3 pi over 2. Now as we take a look at this equation, we're going to find all of the solutions for the equation 2 sine squared of x plus the sine of x equals 1. Now, this has the looks of a quadratic equation. So what we're going to do first is get this equal to 0 by subtracting the 1 over to the left-hand side. So this is going to say 2 sine squared of x plus the sine of x minus 1 equals 0. Now, what I'm going to do to maybe make this a little bit easier on ourselves is I'm actually going to replace these signs in here with a different variable, and I'm going to use y. So let's think about this as being 2y squared plus y minus 1 equals 0, because I think that makes the factoring easier to see. So I'm going to set up my two sets of parentheses. To get 2y squared, I'm going to need a 2y and a regular y. I need numbers that are going to multiply to negative 1, but add up to positive 1 in the middle. So it's going to have to be 2y minus 1 and y plus 1 equals 0. But now I want to go back and remember that these weren't just y's, these were actually sines. So this is going to factor into 2 sine of x minus 1 and sine of x plus 1 equals 0. And now what I'm going to do is take each one of these factors and individually set them equal to 0. So we're going to have 2 sine of x minus 1 equals 0, and we're going to have the sine of x plus 1 equals 0. Now in order to solve this first one, I'm going to add that 1 over to the right-hand side. So we have 2 sine of x equals 1. I'm going to divide the 2 over, so we have the sine of x equals 1/2. And then in order to get rid of the sine and get x alone, we're going to have to do the inverse. So x is going to equal the inverse sine of 1/2. And this means we need to look on our unit circle for where the y value, the sine value, is 1/2. And that happens two places on our unit circle. That happens at the angle pi over 6, and that also happens at the angle 5 pi over 6. Now, as far as solving this other piece, I'm going to subtract that 1 over to the right-hand side. So we have the sine of x equals negative 1. I'm going to get rid of the sine and move that over to the other side by doing the inverse. So x equals the inverse sine of negative 1. And again, we're thinking of an angle on the unit circle where the y value is negative 1. And that happens at one angle. That's the angle 3 pi over 2. But now this one is a little bit different than our last example because it wants all of the solutions for the equation, whereas the last one wanted us to look on the interval from 0 to 2 pi, which meant that we were only looking at our unit circle. So as we're thinking about these angles, as we're thinking about this x equals pi over 6 and x equals 5 pi over 6, and also x equals 3 pi over 2, there's going to be one additional piece that we have to add on to these angles. Because what we have to remember is that all of these angles also have coterminal angles where the sine value would be exactly the same. So we have to account for any extra rotations that we may make in the positive direction or in the negative direction. So remember, sine is periodic with a period of 2 pi. So what I'm going to do is on the end of this pi over 6, I'm going to add 2 pi times n. And what that means is that we're accounting for any positive coterminal angle and also any negative coterminal angle by adding on this 2 pi n, because n means any number of rotations. So it could be 1 positive rotation or 2 positive rotations or a negative rotation or 3 negative rotations. So we're accounting for all of those extra coterminal angles by attaching that onto the end of our angle. And I'm going to do that for all of these. I'm going to put on the plus 2 pi n to make sure that I'm getting all of my solutions. Now, as we're solving these trigonometric equations, we're not always going to be able to use the unit circle to help us out. So for example, in this one where we've got the cosine of x equals 0.7, there's no way that we're going to find 0.7 on our unit circle because that's not one of our special points. So sometimes we're going to have to rely on our calculators to help us out a little bit. So I'm going to fire up my calculator. So the first thing that we want to double check, because we're going to be graphing, is to make sure that we're in radian mode. So then we'll hit our y equals. In my y1, I'm going to put the cosine of x, and in my y2, I'm going to put that 0.7. I'm going to do zoom 6. And I can see that my red line is intersecting my cosine graph at a bunch of places. I'm just going to focus on the intersection points that are happening nearest to the origin. So I'm going to do second trace intersects, that's option number 5, and I'm going to start with the one on the right hand side of the origin. So I'm going to move close to that point and then I'll hit enter 3 times. So that happens at about 0.795 if we round that off a little bit. And then I'm also going to do this other intersection point just to the left of the origin. So I arrow over there close to that point and hit enter, enter, enter. So we get negative 0.795 if we do a little rounding. So we got an x value of about 0.795, but again, we have to count for all of those extra coterminal angles, and we also had an x value of negative 0.795, but again, accounting for all of those possible coterminal angles. That's going to be it for this video. Thanks for watching.